Okay. So last time we were doing reductions and explained what it meant for a problem y to reduce in polynomial time to a problem x. Okay, and so I'm not going to review the definition, but where I ended last time was with another example. I was going to show that the problem 3-sat reduces in polynomial time to independent set. So last time we looked at the independent set problem, and we also defined what 3-sat is. Let me just give you an example of 3-sat. x1 or x2 bar or x3 and x1 bar or x2 bar. I'm not sure whether that's 2, but we'll see later. Or x4 bar. So there's a little question about what that is. And x2 or x3 bar or x4. Okay, so we have 3 clauses. Each clause has 3 literals, and it turns out there are 4 in this formula. There are 4 variables: x1, x2, x3, and x4. So 4 variables. A variable either negated, this is the not sign, or unnegated, x2 is over here, that's called a literal, okay, just to get the terminology right. And what makes this an instance of 3-sat is that they only have 3 literals per clause. It's not the fact that we have only 3 clauses. We could have many clauses. And it's a satisfiability problem. The question is, can we assign true and false values to the variables to make this whole formula true? And I said you assign the values to the variables, not to the literals, because we have the rule that if you make a variable, let's say x2, true, that automatically makes x2 bar false. Okay, so you can't assign truth and false values to x2 and x2 bar independently. They're linked. Okay, now in this particular one, we could, this looks like it's pretty easy to satisfy, right? We could just make x1 true, and yeah, we've got plenty of, if this is an x2 here, we can make x2 false, which makes this true, and then make x4 true. So because ors only in each clause only require a single literal to be true, we just need to see that there's one way of making each, picking one literal that becomes true. And then we have the and between the various clauses. So we need one in each clause that ends up being true. And we have no contradictions here. x1 is true, x2 bar is true, which means that x2 is false, and x4 is true. So it all works. So certainly we can make this true. But the 3-sat problem, the problem is given a 3-sat formula, can it be made true? And we're interested in algorithms that answer that kind of a question. So this is our problem. Let's say it's the y problem. If we look at y reduces to x. So this is 3-sat as our y. Okay. Now, what's an obvious way of solving this? We actually, Michael mentioned last time, which is what? Yeah, you can build a truth table. And what's a truth table? Well, it really is just an enumeration of all possible ways of assigning truth and false to the variables. And if we have n variables, so in a truth table, for 4 variables, there's 2 to the 4th different ways of assigning true and false to the 4 different variables. So 2 to the 4th is 16, right? So we would have a table here which was like true, 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 false, etc., all the way down to false, 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 false. And for each one of these, we could evaluate whether, so this is x1, x2, x3, x4. If you made them all true, would this satisfy it or not? Well, x1 true would make this true. Actually, no, here we wouldn't be satisfying this clause if we made all the variables true. So in this assignment, it would be false. And in the next one here, it would be true, right, etc. And the fact that you have one way to make it true means that there's a way of satisfying this formula. Okay, that's an algorithm. It's certainly constructive. You could program it, and so on. But if we let the if n, let's say, is the number of variables, then this has 2 to the n rows. Okay. And is that polynomial? Well, it's not a polynomial in n. Okay. So that's an exponential function in n, where n is the number of variables. But we always ask whether the algorithm is polynomial as a function of the input size. So the input size here is based on the number of clauses and the number of literals, which is 3 per clause. So the whole input size here is roughly 3 times the number of clauses, as opposed to just the number of variables, which is n. So the number of variables is going to be, what's its relationship to the whole size of the input? Well, every variable shows up at least once, okay? So the total size of the input is certainly bigger than just the number of variables, all right? So if we say that it's exponential in number of variables, we haven't yet said that this method is exponential in the total input size, if the total input size is our parameter. Nonetheless, we can cook up examples and parameterize them so that they get bigger and bigger, so that the truth table method is in fact exponential in the input size. It's not polynomial. Everybody understand the subtlety? I mean, I kind of threw in a wrench here. It would have been simpler just to say, look, that's exponential, not polynomial. But the real thing you have to look at is whether it's exponential or polynomial is a function of the input size. And this exponential is a function of just some part of the input, okay? So, yeah. No question? No, you looked like you were asking a question. Okay. All right, so that approach, that just straightforward building a truth table, is not a polynomial time algorithm. And in fact, nobody knows a polynomial time algorithm, an algorithm that can solve this problem that's deterministic, always correct, and has a worst case running time bounded by a polynomial function of the input size. We just don't know one. Okay, and we'll get some additional evidence later that we probably won't have one, but at least it's certain that right now nobody who's made it public, if they do know it, they haven't made that public. So, and there could be some reasons why people wouldn't make it public, but it's a pretty good guess that nobody really has a polynomial time algorithm for this problem. All right. But what I wanted to show you was that the 3-set problem can be reduced in polynomial time to the independent set problem. The independent set problem was the problem that you're given a graph and you're given a target, and you want to know whether there's an independent set of that target size. That's the way I framed it. And maybe even one bigger than the target size. And again, what's an independent set? It's a subset of the nodes that are in the graph, such that no 2 nodes in that independent set are adjacent. So, to do the reduction, last time we had a formal definition of what reductions mean. Essentially, it means that I have a polynomial time algorithm. I have an algorithm that does some work that can take in any input, any instance of problem y. So here we're going to take any instance of the 3-sat problem, and it's going to do some polynomial time work and create one or more instances of the independent set problem. Actually, it can do this interactively with the black box. And then it's going to feed the instances to the black box that solves independent set, and then based on the answers that come out of the black box, spend some polynomial time to figure out what the right answer is for that instance of 3-sat. And if you remember, we said that the number of calls to the black box is bounded by a polynomial function of the input size. Okay, so in the reduction, we can do some polynomial time work, call the black box, maybe do some more polynomial time work, call it again, etc. That's permitted under the definition of reduction. But if you remember the reduction we did last time, which was vertex cover reduces to independent set, or we did the other way around, one question I should have asked then but didn't, the definition of reduction allows a polynomial number of calls to the black box. But in this actual reduction, how many calls to the black box did we make? Just one. Now 1 is a constant, so that's certainly bounded by a polynomial function. And it's very common that even though the definition allows many calls, as long as the number of calls is bounded by a polynomial, most reductions that we know only make one call, and that's fine. Okay, so in fact that's what's going to happen in the 3-sat reducing to independent set. And I'm going to do this, show you the idea of the reduction just on this particular example. So in comes the input. That's consider this example as an example of arbitrary input arbitrary instance of a 3-sat problem. And my polynomial time reducer is going to produce a graph that's going to look like this. It's going to have one triangle for each clause in the input. So the reducer, which is an algorithm that works in polynomial time, reducer produces one triangle for each clause. In, let's say, F is how I'm referring to the formula. And it labels the vertices with the literals that are in that clause. So this is x1, x2 bar, x3. So this is the triangle for the first clause. And the triangle for the second clause is x1 bar, x2 bar, x4 bar. So now, I guess there was a question here because my handwriting wasn't good enough. This is x2 bar because I have it on this triangle. And then for the third clause, we have x4, x2, x3 bar. And it doesn't matter where you put the literals, but it has to be consistent with the edges that are coming next. So one triangle for each clause. The nodes are labeled by the literals in the clauses. Okay? And then what we're going to have is an edge between any two nodes that are labeled with complementary literals. So x1 and x1 bar, there's an edge there, and x2 and x2 bar there, and this is going to get a little messy. there, okay? And x3 and x3 bar, I guess I can go through here. x3 and x3 bar, and x4 and x4 bar. Did I miss any? So there's an edge between any pair of nodes that are labeled with complementary literals. That is, literals with the opposite sign. One is a knot and one is not a knot.
There's an x3 bar from the first and the last triangle.
Oh, okay, yeah. So x3 here and another x3. Wait a minute. I hit this one and this one? Yeah, I had that one already, yeah. Okay. Okay. So there is an edge between any pair or any pair of nodes labeled by complementary that little ambiguous mark there just to hide the fact that I don't know how to spell complementary in this context. It's either an I or an E, so take your pick. Complementary, by complementary labeled literals, or complementary literals. Okay, this. Okay, then we claim F is satisfiable if and only if let's give this graph a name. Let's say GF. That's a graph that was based on F. If only if GF has an independent set of size equal to the number of clauses of F. Okay? So is that obvious to everybody why that's right? Okay, well, let me go through a little bit of the justification. But first, let me just illustrate what it's saying. So we want to know whether the formula is satisfiable. It's satisfiable if and only if the graph that was just produced, and here's an example of it, has an independent set. And what's the size of the independent set? It's equal to the number of clauses in the formula. So it's equal to the number of triangles. Okay. So yeah, certainly, okay, just one observation before we get into the actual proof. In an independent set, you can only take at most one node from any one of the triangles, right? Remember, the definition of an independent set is that it's a subset of nodes such that no two of those nodes are adjacent. So in the triangle, you can certainly only take one of those nodes. So if we have an independent set that's equal in size to the number of clauses, that means that we have exactly one node from each triangle that's selected for the independent set. Okay? And we also know that you cannot have two nodes selected that are labeled by complementary literals because they're connected by an edge. Okay? So if I do find a subset that is an independent set with one in each triangle, let's say I take x1 there, and then I take x2 bar, and I take x4, okay, that's an independent set of size equal to the number of triangles, size equal to the number of clauses. Okay? And the interpretation is that these are the literals that should be made true. So the variable is set true or false. The associated variable is set true or false depending on whether the variable is negated or not. So this is, I should set x1 true, x2 false, and x4 true. And that's an independent set. That selection is an independent set, and it's also a way of setting the variables, choosing truth and false for the variables, that makes the formula true. Why? Because inside of a clause, the literals are connected by ors, so you only have to have one of them true. And between the clauses, they're connected by ands, so you have to have at least one true in each clause. But if the size of the independent set is equal to the number of clauses, and since you can't have two in a triangle, if the independent set is of size equal to the number of clauses that's equal to the number of triangles, we have one that's selected in each clause. So I just showed you, sort of hand-waving by example, that if we have an independent set of size equal to the number of clauses, then we actually have a way of making the formula true. And just the interpretation is, again, that if the literal that's chosen is uncomplemented, then you make that variable true. If the literal that's chosen is complemented, then you make the associated variable false. Okay? Everybody see that? It's kind of a neat thing. Now, in the opposite direction, if you have a way of making the formula true, then we want to show that there's an independent set that is of size equal to the number of clauses. So what do? We have a way of making the formula true. Let's pick a different one than we had. x3 true, x1 false, therefore x1 bar true, and this one will be false, but I didn't say anything about x2 yet, so I can make that true, right? So I could have, well, we have an assignment which makes this true. Assignment means that you have, I know what's true and what's false for every literal. So this is false. x2 bar is false. Okay, x2 bar is false because x2 is true. x4 bar is, we can make that true. x3 bar then becomes false, and x4 is false. Okay, so we have an assignment of true and false values to the variables, which satisfies this formula. Now, how do we use that to get an independent set of size equal to the number of clauses? Yeah.
Can you pick one true value, one literal that's true for each clause, and then circle it in the corresponding circles corresponding vertex?
Right. You just pick one in each clause that's true, and use that to pick a node in each one of these triangles. You're not going to run into trouble no matter what you pick. Here's the only clause that actually had a choice, but we know that in this entire assignment, we never have a variable and its complement both set to true, okay, because that's not an assignment, that's not a permitted assignment of values. Well, you're assigning values to the variables, and that automatically means that whenever an uncomplemented version of the variable is true, the complemented is false. So if you pick one per clause that's true, where the literal is true, and circle the corresponding node, that will be an independent set, and since you've picked one per clause, it's going to be an independent set of exactly the size we want. So the two directions were really the same. I was only kind of tripping you up a little bit by the fact that in a clause, you might have more than one that's true, one literal that's true, but it doesn't matter. You can just pick one, and everything works out. Okay, or you could have thought of it this way. For everything that was true, circle the corresponding node, and then if you had too many in a clause, let's say we had x4 bar and x1 bar circled or squared. Now you have too many, just erase one. You still have one per clause. And you don't, because this worked out here, you're never going to have complementary variables that are both selected. Okay, so that's a reduction. It certainly just takes polynomial time as a function of the input size to build the graph. You're building a triangle for each clause, and then you're looking for at each label for its corresponding label. All that stuff is rather trivial and immediately implemented in polynomial time. Polynomial is a very big bound, and you can try to be clever about building this graph, but you don't even need to be. For the purposes of reduction, all we care about is that it's polynomial time. So if it takes you n squared time or cubic time or whatever, that's still polynomial. And this thing says that what we do once we feed this instance of independent set into the black box, and it's looking for whether there's an independent set of target size equal to the number of clauses. So this is the target size. So we feed this instance a graph and a target, which is equal to the number of clauses, into a black box. And the outcome's yes or no. Either there's an independent set of that size or there isn't. If the black box says yes, then the answer to whether there's a way of satisfying the formula is yes. And if the black box says no, then the answer is no. So we have, and that clearly, that's polynomial time to interpret the result of the black box. So we've shown that 3-sat reduces in polynomial time to the independent set problem. Okay, so now you've seen two examples of reductions, and the notion of polynomial time reduction is really at the heart of the whole theory of NP-completeness. So now I'm going to get into NP, although maybe I should, actually two things I wanted to say before I get into NP exactly. Y reduces in polynomial time to x, and x reduces in polynomial time to z, okay, implies that y reduces in polynomial time to z. So polynomial time reductions are transitive, okay? This is some polynomial. It produces input of problem y is transformed in polynomial time. Let's say it's function f. So this is the size of the input y. This is how much time the reduction takes. And therefore, the size of the instance that's created, x, is bounded by that. And then the input size x reduces to z, and maybe that's by a polynomial g. It's a polynomial function g as a function of the input size x. Okay? Therefore, y reduces in polynomial time to z. Well, what's a polynomial that we know is big enough to say that y reduces in polynomial time to z? Anybody? Okay.
G of f of y.
Yeah, so g of f of y. Okay? So f is the polynomial that operates on y, and therefore the input size that's created is no bigger than that. And then x, this reduction, its time bound is bounded by a polynomial g, and the input size that actually is given to that, well, here it's denoted as the size of x, but the size of x is at most f of y, and so therefore the whole time for this reduction is g of f of y. So this is a polynomial of a polynomial. But a polynomial of a polynomial is still a polynomial. Okay, you're talking about the size of y. Maybe this f was a square, and maybe the g is a cube, and therefore the whole thing is bounded by a sixth. These exponents multiply, but they still just remain some constant exponent of the input size y. Okay, so reductions, polynomial time reductions are transitive. That's one thing I wanted to point out. And the other thing I wanted to point out, I've forgotten. There was some point I wanted to make, but I'm sure it'll come to me someday. Okay, so the next thing, oh yeah, I know what it was, because I said the next thing was NP-completeness, or NP, sorry. But before we actually get to NP, I should tell you what P is. This is the definition. P is equal to the set of all decision problems. A decision problem is one that has a yes or no answer, which can be solved. And by solved, I mean by a deterministic algorithm that's always correct, can be solved by an algorithm whose worst case running time is bounded by some polynomial function, polyfunction of the input size. Okay, so we've seen problems in P, okay? Although a lot of problems that we looked at were not cast as decision questions, we can typically convert them to become decision-type problems. So, for example, we looked at the problem of scheduling intervals. What was the maximum number of intervals that you could select which were pairwise non-crossing, non-overlapping? That was a maximization problem, but we could just cast it as, here are the intervals, the input is the intervals in some target, and ask, is there a set of intervals that are pairwise non-crossing of size at least as big as the target? That's a yes or no. And we saw an algorithm for that, which was, in fact, linear time, I think. So that's certainly bounded by a polynomial. That's just order n, where n is the number of intervals, and so that's n raised to the 1. So that was certainly a polynomial. And every other algorithm that we looked at in every other problem and its algorithm that solved it that we've seen so far, other than building a truth table, has a running time that's bounded by a polynomial function of its input size. So we're quite familiar with this class P. Okay? That was P of the good guys. All right. Now, unfortunately, not all problems have solutions that are known to be in P, or solutions that are in the class P. So independent set is an example, satisfiability is an example, vertex cover is an example. All of those problems can be solved by fairly straightforward brute force enumeration, but when you enumerate in that way, you get into exponential time. There's an exponential number of possible solutions. So, for example, for vertex cover, the problem was: is there a subset of a particular target size or less, which is a vertex cover? Well, you could enumerate all subsets of nodes of that appropriate target size, and just check each one to see if it's a vertex cover. Now, if you make your target size 5, independent of the input size, then that's a polynomial. It's if n is the number of vertices, the number of subsets of size 5 is bounded by n to the 5th. Okay, But if instead you're considering the class of problems where in comes the graph of size n, and your target is always n over 2, okay, then that brute force enumeration is going to enumerate roughly n raised to the n over 2 different subsets, and that's not a polynomial. Okay, so we have all these problems where we don't know algorithms that put the problem in class P. So there are many problems, actually huge many problems, that are not known to be in P. Okay, now the grammar here is very important. There are many problems that are not known to be in P. That's different than saying that there are many problems that are known not to be in P. Okay, where you put the not, whether it's here or here, makes a very big difference. Okay? Problems are not known to be, we don't know that they're in P, we also don't know that they're not in P, we just don't know. If I put the not here, then that's saying there are problems that are known not to be in P, which means we know that they're not in P. And there are problems like that too, by the way, but the ones of interest to us are these ones that are not known to be in P. Okay? However, for these problems, the ones that we're going to be talking about, they have an interesting property that, however, there are algorithms okay, deterministic, correct, well, correct in a sense that I'm going to, they're correct for what they're designed to do, but I'm going to be more careful about that in a minute. And whose worst case is bounded by a polynomial function of input size, which can check a proposed solution Okay, now I'm going to put all this let's put the whole thing in quotes, which means this isn't quite right. Okay, but this is the intuitive starting point where we're going to start. Okay, and then we're going to make it more precise in a way that is difficult to parse, which is why I don't want to just jump in on the purely technical without trying to give you some intuition of this first. Okay. Now, first of all, what do I mean by checking a proposed solution? So let's think back. Well, take your favorite of these three problems that we've talked about: independent set, vertex cover, or satisfiability. Who has a favorite? Okay, vertex cover, good. Okay, so into vertex cover problem, an instance of vertex cover is a graph. Okay. And a target, 3. So an instance is a graph and a target, and the problem is there a vertex cover of size 3? Okay. Well, what's a proposed solution? In this case, is a subset of nodes. All right. So this one, actually, I was trying to keep my eyes closed, but close enough. All right. So I picked 3 nodes randomly. Okay. That's my proposed solution. Now, is it a vertex cover or not? Actually, amazingly, it is. That's good. But my point is that I can check it. You can check it. Okay? If I said go out and design an algorithm or write a program that can take in a graph, a target, and a subset of nodes, and decide whether that subset of nodes is a vertex cover of size equal to the target, you could easily write a program to do that. And that program would very easily, if you were at all sensible, have a running time that was bounded by a polynomial function of the input size. It's just a rather trivial, straightforward kind of thing to check whether a set of nodes is in fact a vertex cover of the right size. Now let's say I propose those three, then your algorithm would look at it and say, well, there's this edge here that is uncovered, so this is not a vertex cover. Okay, so your algorithm could easily check whether the proposed solution is in fact a solution to the problem. Okay, so what would we do in the case of a formula in 3-sat? What's the proposed solution in that case? So you're given a formula, and we want to know, is this formula satisfiable? What would be a proposed solution? Rupen.
There should be at least a vertex, which is a vertex cover in each AND case, like in every braces. Suppose if we say like these 3 vertex nodes that we circle, and
right,
each of them to make the whole.
Well, okay, you're talking about vertices and circling, but this is just a problem that has variables.
Yes, okay.
Yeah. So what's a proposed solution? Well, to satisfy this, you require one literal per clause to be true, at least one literal per clause to be true. So proposed solution. Somebody else had a hand up back there. Yeah.
Just an assignment of variables.
Yeah, just the assignment of variables. You say exactly which variable you want to be true, which variable you want to be false, and then the program would take that information and check the formula to decide if the formula had been made true or false. And certainly, again, the program, the algorithm that does that checking is fast in polynomial time. That's a rather straightforward, kind of checking. So checking is easy in general, and but finding the solution is hard. I mean, we all know that sort of in general life. This is when somebody shows you the answer. Oh yeah, of course that's it. Whereas finding it can be very difficult. Okay, that's the Christopher Columbus story where Christopher Columbus was challenged by somebody to stand an egg on end, and all kinds of wise men had tried it, and eggs keep falling, and so Christopher Columbus took the egg and went, and it's kind of cheating because it broke the end of it, but it stood up straight, and then they said, well, that's obvious, and yeah, it's always obvious once you not always, but often obvious once you see the answer, but finding it can be difficult. Okay, so the class NP is roughly, and again this is in quotes because this is not the purely technical correct definition, but roughly speaking, NP is equal to the set of all problems, all decision problems where there is an algorithm, a deterministic always right, always correct algorithm that can check a proposed algorithm a proposed solution, sorry. In time bounded by a polynomial function of the input size. Okay. So basically, NP, that's a set of those problems that have a fast algorithm to check proposed solutions. And that's certainly true for independent set, vertex cover, satisfiability, pretty much any problem you can think of a way of checking it. Not all problems, but pretty much every problem you can think of a fast algorithm that can check proposed solutions. Okay? Now this isn't always true. Suppose the problem is primality. Primality is you're given a number and you want to know, is that number prime or not? Okay? So what is a proposed solution? The word yes or no. Okay? So you're given this gigantic number, and the decision question is it prime or not? And we don't have a nice algorithm for that, say. Do we have a nice checker for that? If the proposed solution is the word yes, does that really help you? You're back to the same problem. So I can't say every problem is an NP, although actually primality is an NP, but we won't get to that. When we properly define NP, it'll be more plausible. But right now, NP is roughly this. Okay, most problems are clearly going to be an NP because they satisfy this, and some problems are not obviously an NP, but we'll see that when we give a more precise definition, it'll be more plausible that they are an NP. So you can think of this. You can think of this definition of P and this definition of NP, and that will be proper and correct for, certainly every problem that we look at in this class, and 99 point how many nines of all the problems that are either in P and NP. These two definitions are perfectly fine, but they're not actually perfectly correct. Okay, and so next time, I thought I would do it this time, but I didn't get that far. Next time I will do the correct definition of NP, which is weird and technical. So I didn't want to start that way because then you wouldn't have any intuition. But if you get this part today, then you've gotten the intuitive part of it.